Toil comes from becoming occupied with tasks that feel unnecessary over a period of time. Toil comprises of tasks that can generally be automated or avoided. We invite you to come along and take a deep dive into what toil is and how it affects your teams. Particularly, we will focus on toil arising from poor alerting practices. Hello, and welcome to this series of on-demand webinars from Plumbr. In this series, we'll be breaking down some common problems that engineering teams have. We'll also proceed to illustrate how these problems can be solved using Plumbr. In this session, we'll focus on toil for DevOps teams. We'll define what toil is. We will then go over a few aspects of what everyday actions contribute to toil. Finally, we'll see how using Plumbr, our real user monitoring tool, can help alleviate engineers from toil. Defining toil is like a parable of the blind men and the elephant. Each organization and each team has their own definition, and each engineer on a team may view different activities as toil for themselves. The best way to understand toil, therefore, is to find a common denominator. From this common denominator, we can illustrate the concept of toil with some example activities. Characteristics of activities that comprise toil can be inferred from their mushrooming costs. When dealing with toil, the costs that engineering teams typically incur are cost of context switches, cost of building automation, and peripheral costs such as keeping up morale and handling frustrations of individual engineers. The Google SRE book defines toil as being tasks that can be manual, repetitive, automatable, tactical, devoid of enduring value, and that scales linearly as a service grows. If any activities currently undertaken by your team have these characteristics, then they definitely fall under the category of toil. Another important way to understand what toil is: any activity that the team considers necessary, but would like to expend less time and effort in doing. Let me explain. All DevOps teams would like to reduce toil. All DevOps teams understand that eliminating toil completely is unrealistic. Therefore, reducing it is a more pragmatic and mature goal. One of the responsibilities of an engineer on a DevOps team is ensuring that new features make it to production on schedule. To be able to release continuously, a team needs tools for revision control, build processes, automated testing, and deployment. One engineering team, who were in the process of making their move to DevOps, decided to optimize their release cadence by adding unit tests and improving test coverage. Now every time they need to release some code into production, they go through a set of automated build and test processes, but have to wait for an engineer to carry out the actual release. This amounts to toil for the engineer responsible for deployment. As more features are built and more software needs to be released, the engineer would get exhausted just from releasing various artifacts. This can be easily alleviated by first adding automation to releases and then improving test coverage. One of the sources for toil among engineering teams is poor alerting. We often hear complaints about alerts keeping engineers up at night. Personally, I would hate alerts that kept me from doing things during the day as well. Whatever time of day it is, undesirable alerts are, well, undesirable. Within the on-call rotation, a major part involves receiving and responding to alerts. If alerts are not designed or implemented correctly, a lot of toil can arise. Poor alerting can manifest in three distinct forms. The first, too many alerts, leading to alert fatigue. Second, alert flapping, where there is an on-again, off-again scenario. Lastly, no alerts, when an alert is not issued for a critical condition. A lack of processes within the organization to shield you from these ill effects can create a truly toxic environment. Recovery from this can be rather difficult, and so preparedness and preventative measures become very pertinent. Let us explore the three themes in more detail. Oftentimes, even when you're dealing with an incident, you'll see many alerts go off about various systems. This leads to fatigue quickly. Having too many alerts is also a symptom of false positives. False positives are a rather common problem in the whole software industry. False positives, which result in too many alerts, are a bottleneck to releasing new features or working on improving existing ones. False positives can quickly become counterproductive to the whole mission of a team. Reducing false positives is a crucial part of a good monitoring setup. This is because the cost of an alert is quite high. Context switches, lost time, communication between teams, rising frustration of engineers, and meetings all quickly add up the cost of each false positive. Mentally, engineers get drained addressing these alerts. They will quickly start to ignore them, and this will cause them to miss some important stuff, essentially putting the ROI from alerting to zero. Therefore, solutions must minimize the number of false alarms as much as possible. Here's an example of a situation where the engineer faces too many alerts. Assume that you're running a web application on production with AWS. You have a standard setup and a scaling policy that determines when your auto-scaling group should scale out or scale in. However, what if you didn't set the scaling policy correctly? What if a bad threshold was picked? Here's the way this would play out for your team. Your host will issue alerts about CPU memory exhausting. An increasing number of 5xx responses will trigger alerts from CloudWatch. Pingdom checks will begin to report increased load time or failed responses and send you alerts. Application logs will begin to log more errors. Any log monitoring will begin to issue alerts based on this. Increased logs could also trigger disk I/O alerts. There may be many more other alerts that would be triggered. While all these represent problems, the fundamental problem here is a poor scaling policy. Getting alerts for the root cause may not always be possible. However, this is not an excuse to overwhelm engineers with alerts. This situation is also illustrative of how context switching, alerting setup costs, and the cost of response and diagnostics can quickly add up. Having a poor signal upon which the alert is based is at the core of this issue. Let us look at the other scenarios too. Creating too few alerts or setting thresholds very high can cause you to miss key errors, failures, or latency degradations. In some cases, they are known as false negatives. Let's look at some examples. All the alerting and monitoring mechanisms are optimized for certain system parameters. Let's consider CPU utilization. Within any 10-hour window, CPU utilization must remain below 80%. Another example, 99.9% of DB queries must span less than 1 second. These parameters may never be violated, and yet there will be problems with our application. Oftentimes, users are unable to interact with applications, and external systems may have problems with the API. This never shows on the radar of our monitoring systems. This leads to excessive finger-pointing between subteams or individuals when things go wrong. But users will continue to have a tough time, and there would be no way to acknowledge the problem or begin to investigate. Many situations give rise to false negatives. Here's an example. Check the alert history of this sample Nagios monitoring setup on an example WAN. There's a check that runs every 30 minutes. This is an alert that works on a fixed schedule. It pulls the WAN for a health check and reports the result of this check as an alert. Because of the 30-minute space between each check, there isn't enough granularity to catch problems in flight. This causes an alert after the system has been down for an unknown period of time. The deficiency is in a poor design choice in the granularity of the time interval. The result is that an engineer does not receive an alert about a fault in their production system. Another place where false negative often arises is from peripheral systems or integrated systems. Traditional monitoring and alerting will not help because monitoring the peripheral systems does not fall under the direct purview of those tools. If one of our applications uses a third-party JavaScript library and it takes too long to load, foo.js, typical monitoring, which only looks at our systems, would show all systems normal. Under-alerting can also come as a consequence of alert fatigue. With limited ability to sort the true positives from high volumes of alerts, engineers snooze or suppress them. This leads to no alerts when the small issue was symptomatic of a larger system-wide failure. Alert flapping is a situation when infrastructure or services change states too frequently. This causes a storm of alerts and recovery notifications for engineers. This leaves engineers in a situation where they have nothing that tells them if a situation is urgent, important, actionable, or even real. Alert flapping can make engineers snooze alerts about ongoing or imminent problems with a service. This can result in an issue of much higher severity arising soon after, about which they will get no alerts. Here's an example of alert flapping on an infrastructure side. Assume that you have a job that runs periodically. Every time it runs, it occupies a certain volume of disk space. It is designed to run for 6 minutes every 4 hours. When it runs and is nearing completion, It fires off alerts about running out of disk space. When the job is completed, the situation is normal, and all systems return to normal operations. But 6 times every day, engineers are alerted to exhausting disk I/O and a return to normalcy. This cannot be a good thing. This will quickly lead to fatigue and remain a distraction for the engineers if left unchecked. In summary, the complexity of the monitoring, alerting, and overall incident lifecycle in DevOps can result in either of 3 cases. Too many alerts, which can distract engineers. No alerts triggered, which can cause incidents to be missed. Flapping alerts, which would add no meaningful value. Striking a perfect balance is nearly impossible. So, what goal should teams strive for? Bear this question in mind for a minute. Poorly designed alerts have a very direct economic impact on the organization. Having engineers overspend time on issues that they cannot find or reproduce, or that aren't issues in the first place, will cause engineering efforts to be taken away from other important tasks. What matters to teams is the ability to resolve errors and performance issues quickly. When this is not achieved, users are impacted more. When users are impacted, it leads to the business as a whole being impacted. So, what can unify the product, usage, and infrastructure, and serve as an appropriate proxy metric? The real goal is making sure the end users of the software are satisfied with the application. Therefore, alerting and consequently monitoring should also be built on the basis of users and usage. Product development and engineering boast of user-centric design principles. Why should monitoring and alerting be left behind? All metrics that matter to the performance and availability of an application can find a direct basis or proxy metric in users or usage. The solution, therefore, lies in creating a monitoring and alerting mechanism based on real users or usage of the product. Here's another reinforcement of the solution. An engineer gets paged. She wakes up and reads that there is an alert about a server running out of disk space. She runs through her first set of operations in the on-call runbook. By then, she discovers that between getting the alert and now, the load balancer had already begun to reroute traffic from the affected server. The total number of affected queries was quite small. In hindsight, it was not an issue of high severity at all. All of these events that we have taken as examples suggest that the signal needs to be stronger. A better separation of the important alerts from the noisy ones that arise is required. An important source for an alerting signal, therefore, is to use data from real usage of application. Real user monitoring places the focus on users and usage as opposed to system-level behavior. This forms a more objective basis for alerting. No one can deny that if users are affected beyond certain levels, engineers must take note and begin investigating for fixes. Whether the root cause may be database issues, CPU provisioning, scaling policy on the POS, or a third-party infrastructure failure. If users are affected adversely, it is reasonable to alert engineers. This is one of the problems that we set out to solve when building Plumbr. Plumbr works at the intersection of application monitoring and real user monitoring. Because Plumbr builds on data that is collected from real usage, it is the most accurate reflection of what a user experiences when interacting with web applications. Plumbr monitoring works irrespective of what technology powers your application. Plumbr's application monitoring capabilities are built by tracing each API across distributed stacks. Complete exposure of the availability and performance characteristics of digital services is available when you attach Plumbr agents to your applications. Plumbr can also be configured to alert engineers on the basis of degradation in experience for users. If error rates or response times shoot above certain thresholds, Plumbr alerts can be configured to go out to engineers. Here's an example application whose interactions and error rates are plotted over time. Alerts can be configured to go out on sustained or increasing error rates. Plumbr monitors user interactions and can facilitate arithmetic of error rates based on interactions, sessions, and users, which translate to alerts being fired when the error rates shoot up here and here. Another example basis for alerting could be this. If failed interactions exceed 5% of total interactions, an alert can be issued. This would mean that the experience is degrading for a significantly large fraction of users. Plumbr will allow you to break down the alerting on a per-service basis. Surely, some services are more critical than others. For these, you can adjust the thresholds to be different. That is, you can check Plumbr monitoring data to see if the service fails for 5 users. you can then issue an alert. Plumbr therefore adds meaning by allowing you to tie these alerts to specific SLIs and SLOs, which will make the alerts way more meaningful. In addition, Plumbr can work with existing toolchains. Here's an example of a Prometheus rule that can be constructed. Let's build an alert when the error rate is too high for users. Here's an expression. What does this tell you? This is the basis for an alert. When the total number of failed API calls exceed 0.5% of the total number of API calls, we configure an alert to be issued. Here's an example of another service. So the most objective basis for alerting is achieved by defining the basis for alerting with the importance of a particular service and then configure numeric thresholds based on usage. Watch the table on the screen. You should build a list of services and assign thresholds as you see fit. Alerts must be sent out when these thresholds are violated for each of these services. This will help make it very easy for engineers to differentiate what they need to act on immediately versus leave for later. When only meaningful and relevant issues are brought to their attention, their time and energy are only spent on resolving urgent and important issues. This will automatically reduce the toil that is felt when being on call. We've seen how Plumbr can help relieve engineers from expending toil. DevOps teams are usually asked to construct a toil budget and match their activities against this toil budget to see how much they are exhausting with each of their efforts. While that aspect is beyond the scope of this video, what's important is that engineers become aware of the techniques that can be used to address the never-ending paths that can exhaust toil quickly. To conclude, meaningful alerting reduces toil automatically. What's meaningful may differ for everyone, but making it user-centric is a simple way to find common ground. Monitoring for user behavior gives the data upon which to build alerts that reduce toil. All these benefits can be had by using Plumbr. Head to plumbr.io and claim your free trial today. If you'd like to speak to us about any aspects related to how this can apply to you, please write to us at info@plumbr.io. We focus on alerting today. We'll focus on many more aspects in upcoming videos. Stay tuned. Thanks for watching and have a great day.